Should be live. Double check.
Check. Still checking. Yeah, we're live.
Hello and welcome to today's episode of Courtcast. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So, Tim and Mikey, I thought this would be a really interesting episode in light of the news that came out from Google about their, new super powerful quantum computing chip called Willow. And so we've discussed quantum computing in the past. So I thought it'd be nice to revisit this. So, Mikey, I'm going to turn this on to you since you look very eager. Could you describe to the audience, at a basic level, like what quantum computing is before you even talk about the crux of the meat of the topic?
Yeah, sure. So we talked about this in the past a bit, but I guess we're doing a full episode on it now, given the new results. So as you may know, it's all over the news. Not just this result, but literally for the last 5 years, at least my Google News feed is just full of basically overblown claims, like kind of hyping up this new technology called quantum computing, and it's supposed to revolutionize technology and do all these great things. And basically, it's as we all know, like a normal computer computes by essentially encoding information into binary, into bits, zeros and ones. So those are like the fundamental units for storing information in a normal computer. And quantum computing offers a way to kind of go beyond this binary framework by taking advantage of quantum mechanical logic, in which a state can not just be 0 or 1, but be in a so-called superposition of both states. So it essentially allows you to access like a larger information space and do certain computations more quickly than you could using this limitation of binary encoding. And so I think it's important to note that this new way of storing information that goes beyond binary, it's not like just a guaranteed speed up of certain, it's very specifically certain calculations that become possible to perform using this new technology that isn't possible in binary in a normal kind of time span. So I guess that's basically just like an overview.
Yeah, could we give the audience some intuition about like why superposition is like gives a greater computational capacity, for certain kinds of problems, but like why does superposition even matter? Like what's the big deal? And like how, being in a superposition of like 1 and 0.
Yeah, I think very, very loosely, it provides a way of sort of like parallelizing your computation, right? So in a normal computer, if I wanted to search a space, let's say like there's like a let's say I have like a simulation, like a virtual reality simulation. Uh, I would need to encode each point in that space with a bit of information and essentially do the computation linearly. But storing information in a superposition of 0 and 1s allows you to sort of access different parts of the space simultaneously and sort of parallelize your computation and achieve the result much faster than would be possible through any kind of like linearly scaling.
Yeah, I think I can add a little bit of extra information. I know we've been talking about quantum physics for a long time. One of the most sacred laws of quantum physics is the preservation of possibilities. And when we talk about superpositions and all that, we can think of it as a quantum mechanical state has all kinds of possibilities. In fact, this possibilities grows exponentially. The more quantum bits you have, the more the combined possibilities are. And when you do computation on all these possibilities, you can do it all at once, basically, as opposed to say, hey, let's try 0 or 1 or 0, 1, 1, 0. You can try all of them at the same time. And that's sort of the dream of quantum computation, is to do everything almost all at once.
Mhm. Yeah, maybe it might be helpful to give a concrete example of like maybe some of the more well-known like algorithms that you can do only in a quantum computer, not classically, and maybe what they help you do faster and more efficiently. I guess Tim or Mikey, I'll point this question at either of you, whoever feels compelled to answer.
I think the first example where it was demonstrated that this new kind of computing can provide an advantage came from just simple search algorithms, right? So, like I mentioned, if you
Mhm.
wanted to explore like the possibility, like if you wanted to explore what are all the possible words you can make with a 26-letter alphabet, right? It would take
Mhm.
you a long time to try every single combination. Um, and so, yeah, quantum computing, as Tim mentioned, like allows you to sort of search multiple possibilities at the same time. So, doing this kind of like random sampling or random search, that's the kind of algorithm where you really get like a huge speed up. The other famous example is Fourier transforms, which classically
Mhm.
requires like I think it's n squared time because you essentially have to search a matrix or half a matrix since it's symmetric. Yeah,
Mhm.
quantum computing allows you to kind of search the entire space of matrices all at once. So search and parallelization are really the two areas where this gives a great speed up. And
Yeah,
that's
I
really
can.
important. It's almost famously noted, like for cryptography, right? If you're trying to break a password, you have to try like every single possibility brute force. That's essentially a search problem, and famously, quantum computing will allow you to like break uh, codes that are considered robust now.
Yeah, I think one of the prime example is the NSA encryption, which relies on the idea that it is much easier to multiply two very large prime numbers than to factor them. In quantum, if you encode the information of prime number of an integer in a quantum state, instead of trying one prime number at a time to see if you can factor them, because there are really no like easy algorithms. You just have to, even the fastest algorithm, sometimes you have to sort of brute force it. But in quantum physics, you can try sort of multiple candidate prime numbers at the same time, and using a lot of tricks and whatnot, you can factor prime numbers a lot quicker. So in a sense, when quantum computing is fully realized with the full power, millions and millions of qubits, yeah, the current state of the art encryption algorithm will probably have to be completely redone, broken.
And maybe it's
Yeah,
also we
yeah,
should
yeah.
kind of talk about like the hardware because like everyone talks about quantum computing as though we're talking about like a regular desktop computer, but like the quantum version.
I,
But I think what's kind of like
Mikey,
yeah.
one small correction I want to make. We'll definitely want to go down this train of thought.
Yeah.
The algorithm is called RSA. Just small correction, Tim, instead of
Oh,
NSA, RSA. But
Oh,
yeah, go ahead. No worries.
yeah, most heavily used by the NSA though. So it makes sense.
Might as well be the NSA.
Yeah. I mean, they're basically the dominant force in terms of organizations with the capability of even attempting this kind of a brute force calculation. But yeah, I think one thing that's kind of like often overlooked when we talk about quantum computing as though it was like a regular computer is that when we look at a regular computer, we said stores information as zeros and ones. And if you look at the hardware, this is often realized through like technology like transistor technology, which is essentially a wire. And a wire can hold a charge, and depending on the charge, that can either be a zero or a one. Um,
Mhm.
in quantum computing, we're talking about going beyond using transistors and literally using elementary particles to store information. So, we think it's not just like, upgrading from a normal computer to a quantum computer. We're talking about literally using atoms, electrons as
Mhm.
the fundamental storage units. And this requires the ability to essentially manipulate elementary particles at our will. To make a quantum computer, we have to have such a control over the behavior and movement over elementary particles, where we can essentially treat particles as though they're like wires in a transistor. Um, so we're
Mhm.
really talking about having almost like a godlike control over like the fabric of reality in order to fully realize quantum computing. So people talk about RSA encryption, all the great things. Yeah. Sorry.
Oh no, go finish what you were going to say.
Yeah, I just wanted to make like it's way easier to simulate a universe. It would be way easier to simulate a universe on a quantum computer than it would be to break RSA, right? Like in order to break RSA encryption now, we have to use brute force techniques where we try all the combination. That requires like a masterful orchestration and control over these wire transistor hardware. We're talking about achieving that same control over literally fundamental elementary particles. Is no easy task.
Yeah. No, it's interesting. So I guess like, Mikey, could you walk us through kind of like maybe high level how a quantum computer actually works in terms of like I have a bunch of particles. Do I send like electromagnetic wave and they like change and then I measure something, or like how would let's say I gave you a quantum computer, like how would that work?
I think so. The technology, there's a bunch of different routes that people are attempting to use to get to achieve this. The most popular route, just because it relies on technology that exists, is the so-called superconducting quantum computer, and that's essentially like it's kind of like the stupidest way to approach it. Like essentially like upgrading a normal computer into a quantum computer. You're essentially like creating transistors, but instead of wires, using currents in a superconductor medium to store information. So it's really trying to quantumize a normal computer, and this runs into several problems. Just because if this was the smartest way to manipulate elementary particles, then probably God would have chosen that method, right? But it's really modeled after like current existing classical hardware. Other approaches, seemingly more promising approaches, are like using actually photons of light. So there are light-based quantum computers that people look at. Some of the best results have come from so-called like trapped ion quantum computers. I don't exactly know how that works, but in terms of the details. But and then of course there's Microsoft's approach, which is the most ambitious of all, where they're actually trying to create a new kind of fundamental elementary particle called an anyon to store information. That's a very, very ambitious program, and that's probably the closest thing to what would actually work. But right now, we're still stuck with these startup companies that are essentially trying to take classical technology and quantumize it.
Okay, yeah, that makes sense. So it kind of tying this back to the original thread of this discussion, which one is Google using between these four different methods I think that you mentioned?
Yeah, I believe it's the superconducting approach. Yeah, and which I've talked to several people who work in the field, and they have very little confidence that this is really the route to use to get to full-scale quantum computing.
Oh, why superconducting? Like, why do you even need to bring that in?
Yeah.
Why does it? Yeah.
I think it's just that when the temperature gets too well, I'm not sure about the superconducting bit, not an expert, but one of the biggest hurdle of supercomputer is that it's noisy. Basically, the superconducting nature. Huh?
You said supercomputing. You mean quantum computing?
Yeah. So well, I was gonna say, yeah, I'm not sure about the superconducting aspect, but generally, yeah, to maintain quantum mechanical properties, it's very hard. And in a normal day lives, a lot of quantum mechanical properties are almost removed by the air molecules. Basically, the quantum information or the possibilities are spread out to the environment. And that's extremely detrimental for a quantum computer. For example, if you're trying to do a computation, and if the computer interacts with air molecules, it could just totally screw up that computation. So one way to fix it is to reduce that noise. And the easiest way to do it is to cool the thing down so that it's not interacting with the environment as much. And I imagine making things superconducting sort of gives you that quantumness. It sort of enhances the quantum mechanical properties so that it stays quantum mechanical longer. And this is measured in like coherence time, what we call. and I think it's in the microsecond regime. So it's not very long. I mean, can you imagine a computer that only lasts less than like a fraction of a millisecond? Like that's not, you can't do calculation. Like imagine I'm doing a calculation, whoops, it's a millisecond, it's gone. Like you're done. So that's what we're talking about here.
Yeah. So before we proceed, I want to read an audience question about something we mentioned a while back. How does this work with the uncertainty principle, meaning controlling elementary particles?
Yeah, let me take a stab at this. The issue, we have to keep in mind what the uncertainty principle says. The uncertainty principle says that if you measure two properties that are incompatible in quantum physics, there is always an uncertainty related to how both are measured. A quantum computer gets around that by, first of all, you don't do measurement on the computer state until the very, very, very end when you demand a result. And when you do make a measurement, you only measure one thing. You don't measure multiple things. In some sense, you don't get sort of the penalty from the uncertainty principle.
Got it. That makes sense. I mean, like when people first learn about uncertainty principle, they learn, no, you can't measure like position momentum, which is technically two things. But here you're just saying it's only one thing you really need. So uncertainty principle isn't necessarily like as pertinent. Is that fair?
Yeah.
Okay. So I wanted to jump into Tim, you were talking about noise and how I also would agree that I think the reason for superconductivity is to most from the cooling aspect is to like reduce the thermal noise. Oh, what's the reason? Were you saying something, Mikey?
No, I just coughed.
Oh, okay. So and yes, you can do that, but I would still assume that there is noise, like coming from somewhere, and probably there's an irreducible amount of noise in quantum mechanics. So can we talk about error correction, what it is, how it's used, and like, what does that look like? And is it important for quantum computing? So I guess Tim, I'm going to point this one to you since I've been picking on Mikey for a bit.
Yeah, and yes, of course, one of the biggest noise is coming from the environment, and that's probably the biggest one. But I would argue that even if you remove the environmental noise, fundamental physics just is noisy. Like a particle could emit a photon, and just because it's charged, and it could screw up your calculation, and that's irreducible in some sense. But then sometimes calculation, you cannot tolerate this error. I think in traditional computer, we can tolerate something like 1 in a billion or something like that. And there are ways to sort of correct the error, to know that, hey, when an error has happened, maybe you can correct it, or maybe you can let the person know that, hey, here's an error, try again. And so error correction is absolutely critical, and that's also one of the reasons for the hype for the Google announcement, is that they manage a milestone in correcting errors, but we'll get into details in a bit.
So can we describe like how error correction works in a nutshell, not too specifically? You know what, Mikey, I'm going to put this on to you again. You look eager.
As Tim mentioned, error correction is it's not just an afterthought. It's absolutely fundamental to the proper operation of even a classical computer. I just want to mention something about the superconducting thing too, just to go off what Tim was talking about the noise generation. It's very important to just highlight what Tim said about when you do the computation, you set it up, but you don't look at the answer until the end. So you can imagine that in a normal computer, right, you have transistors, wires that can store 0 and 1. But if I were to, like, let's say, raise the temperature extremely high, that wire will start to fluctuate between 0 and 1 in a way that I don't intend. So any kind of heat is an interaction, and any kind of interaction for a quantum computer is noise. So that's why for the superconducting route, it really requires like this almost zero temperature environment where you can be absolutely sure that your computer is shielded from the environment and there's no trying to minimize the amount of fluctuations and heat that is essentially created during the calculation. But from what I understand with the superconducting technology, the actual calculation itself creates heat and noise. So you're actually destroying the computation through the same process you are using to try to perform it. So that's why my friends in the industry tell me that this is not really a promising approach. But to go back to your original question about just how error correction works, it's really the dumbest, kind of the dumbest thing you can think of, but also the coolest thing. We correct errors just by redundancy, right? So if you know that a certain piece of information is unreliable, what's the stupidest thing you can do? You can send 1 million copies of it. That way you know that if like half of them get screwed up, your answer still survives. But it's not exactly obvious that this should work. The reason we have been able to take advantage of this so successfully is due to the results of some dude named Claude Shannon, who some 50 years ago showed, like, because, right, like if I want to send you a message, but I know that someone's going to intercept it and scramble it in between, I could send you, like I said, like 1 million copies of the message. So that way I can be sure that at least one of them gets through. But that only works if I know that each copy is itself reliable. If I send you 1 million super unreliable copies, you'll just get 1 million copies of junk. But Claude Shannon, his master's thesis, he showed that specifically if each message error rate is below a certain threshold, it's guaranteed essentially that you're going to get some kind of robust message. Or what he showed is that for a linear increase in redundancies, like meaning like as I send you more copies of the message, you actually get an exponential reduction in the noise in the final message. And that exponential reduction is absolutely crucial because it means that I essentially can approach zero noise-free answers. And similar logic holds for a quantum computer in terms of like the requirements for the fidelity of each copy and the redundancy. And so that's essentially the crux of the big news, is that Google has achieved just the very, 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 very basic first step in demonstrating that this principle does apply for quantum computers and not just classical computers.
So actually, Mikey, one thing I wanted to ask you about, because this is the way I heard it, is that like before people would just keep sending the same message like X number of times, and then if one message corrupts, but the other ones are fine. You just simply take an average, and then you're like, okay, this is probably the message they wanted to send me. But I was under the impression that Claude Shannon's work was like, no, you actually don't need to send the message multiple times. You can just send the message once, but tack on these like extra correction bits that keep track of like specific properties of the message that you want, say, intact, and also assume that those correction bits can also be compromised as well. So it's like you can figure out where in your message got compromised. So that was my understanding. Is that similar to like what you're trying to say, or I just want to make sure we're on the same page? Okay.
Yeah, I think we're saying the same thing, it's just in different ways. I think specifically, so like you mentioned, your first proposal, just sending a bunch of copies of the message, you could just cross your fingers and hope for the best. But what Shannon showed is that no, you don't have to just cross your fingers and send 1 million copies. I can tell you exactly how many copies you need to send, or how much of redundancy you need to achieve essentially zero error-free computation. So it's like a recipe for describing what you're saying.
Yeah, but
gotcha.
I would say the redundancy is not a straightforward copy, right? It's embedding your information in usually like a higher dimensional space, for example. And the same principle is true in the quantum realm, as opposed to you can argue that a qubit has 2 dimensions, ones or zeros. The way to do it is to embed one qubit into multiple qubits. So instead of having 2-dimensional, you go to 2 to the n dimensional. For example, you can use 5 physical qubit to error correct 1 qubit. So you embed 1 qubit which has 2 dimensions into 2 to the 5 dimensions. Hopefully, the error reduces. But let me just add that for theoretically it makes sense, but for a long time experimentally no one has even demonstrated this, because like, you know, maybe each qubit is so noisy that the more qubits you add, the more noise you add. It's not clear that noise actually gets reduced. Maybe the more you add, the noisier it gets. It's just a hard part of errors. But I guess the breakthrough really, truly from Google is they show a reduction, but it's not that much of a reduction. It's by a factor of 2. They show that if you add 1 qubit on average, the amount of error reduced by a factor of 2.
Huh. So are you saying like so if I have like let's say 1 qubit and then 1 error correction qubit, if I had a second qubit and let's say the error was like 50%, that'll make it 25% error. Is that how I interpret the results?
Right, exactly. And keep in mind that we're still far away from practical quantum computing. Like in the paper, they quote, they have errors of like 90, they have accuracy of like 99.99 or something. But traditional computation requires something like 1 in a billion. So if you add 1 qubit, it reduced by a factor of 2, we're still a few million times off. Let's say like 100 million or something, right? So that you can do a little calculation. That means you need like something like 20 qubits to form one actual error corrected qubit for that to even work. So we're still ways away, but like it's the first step, basically.
Yeah.
I see. So
it's really important. Yeah. I think the part of the goal for this is to, I don't know, douse a little cold water on the hype, right? I mean, I don't know about you, but my Google News feed is just like nonstop full of quantum computing is going to be here soon. Oh, Google breakthrough means that soon we're going to have all this great technology. No, we're really talking about the very first baby step of like using almost like a handful of bits. We're not even talking about like way before the state of actual computing was in the 60s and 70s. So we're like in the almost like in the 1930s era.
And just to kind of put this in perspective, we'll talk about scaling in a little bit, but let's just suppose that this held as you like, scaled it up to like, millions of qubits. What you're saying, Tim, is that like to get the 1 in a billion, error rate that we have for classical computers, each 1 qubit needs to be, accompanied by 20 error correction qubits. So that means if you have like 1 million qubits, you need 20 million error correction qubits to accompany those 1 million qubits. Is that correct?
Yeah,
assuming scaling and stuff, which we'll talk about a little bit.
Yeah, of course. And this factor of 20 maybe doesn't sound too terrible, right? Like it's 20 million versus 1 million. But I mean, the question really is getting to 1 million. Like just look at how large that Google chip is. Like it's macroscopic, and it's got like 100 or so physical qubit or encoded or corrected qubit. I don't remember. Imagine we need to make millions of that. Like how do you even like? You're gonna run out of space. Like you can't have you can't have qubits that far away and still maintain quantum mechanical property. So you can already say that like Google's Willow chip right now, there's no way it can scale to 1 million. It just full stop. Like you can't do it. Like sure they show that you can reduce error by a factor of 2. You add a qubit, but you can't add 1 million of them. Like there's still a block, like a physical block that you just can't jam that many qubits in such a small space. So I would say, like the demonstration really is just a in principle demonstration, not in practice demonstration.
Yeah, and also like the one thing I heard is everyone's heard of Moore's law that computing power doubles every like such and such. I think the quantum analog of that would be like adding 1 qubit essentially. Would you guys agree with that?
Yeah, it's sort of reversible. Moore's law says that the size of these transistors has been historically undergoing like a linear reduction, right? So things are getting smaller and smaller and smaller and smaller.
Mm.
But I don't know
Well,
what
exponential reduction, but yeah.
yeah. I don't know what the popular opinion about Moore's law is, but like people like to extrapolate. Oh, does that mean that like
Yeah.
in 10 years we're gonna have things that are like 10 to the minus 20 in size? No. We're very quickly reaching a point where Moore's law will end. It has
Yeah.
to end because you can't keep subdividing space smaller and smaller. Eventually you get into quantum mechanics. And then I would say it's sort of like Moore's law is essentially destined to be reversed, right? Things get smaller and smaller and smaller and smaller. But then when you reach the quantum level, I guess the analog to Moore's law would transform to like this addition additive process. So it's kind of interesting. You pointed that out.
Yeah. Yeah. And then so Tim, I just want to, quickly go over what you just said. So the main issue is that in this chip, it has maybe 100 or so qubits. And if you assume that like this is the chip and you were trying to scale that up, there's just no way you can have a million chips and have them all be together and maintain their quantum mechanical properties in that way. Is that correct?
Absolutely, yes.
Yeah.
There's a paper where they actually calculated how many qubits you would need to do the kind of computations that we're interested in, like breaking RSA. And I believe the number is in like hundreds of billions. So if we were to attempt to use the current technology to scale up, you would need a computer like the size of the planet to run this. So it's not a feasible line of inquiry, I guess I would say.
Yeah.
Yeah.
Well, so I mean, we do have to comment on one thing, that Google did claim that they were able to do one computation for quantum supremacy, called the quantum circuit simulation. But we can discuss about that. It's completely, to put it short, it's complete bunk, basically.
Yeah, I just want to make one comment that this is kind of reminding me of the pre-transistor days of computer with vacuum tubes and stuff, where they had these huge rooms for like, it's essentially kind of what's happening here at the moment. So yeah, actually, Tim, great you mentioned. I completely forgot to talk about the problem that they have solved that would take like some septillion years on a classical computer to do. Tim or Mikey, can we describe like what that problem is and like, why was it faster to do it on this chip? Yeah.
So I think that statement is kind of sinister. The people who don't know, it will sound incredibly impressive. But if you dig a little deeper, it's that statement has some academic values, but it doesn't have any real meaning. I think to claim that as quantum supremacy, and yeah. So sorry. What was the question again?
Oh, my question is like, what was the problem that they said, oh, we're able to solve it so much quicker than a computer? Like, computer would take longer, a classical computer take longer than the age of the universe. But look at us with our quantum chip, we were able to do it like, in no time at all.
Yeah. So what they did was called the quantum circuit simulation. And to put it nicely, that's literally what a quantum computer does. Because quantum computer, you write quantum computing code, which is a circuit, and like they're literally doing that, maybe with some bells and whistles, right? They're basically randomly sampling what things would look like if you have a quantum circuit, which is literally what a quantum computer do. And if you go through the calculations and say, if you were to do it on a classical computer, and also without any tricks, bells and whistles, just brute force do it, it will be it will take, I don't know, the age of the universe multiple fold. Of course, if you just go to the math, it seems obvious, right? Like, let's say you have 100 qubits, that's like 2 to the 100 dimensions or whatever space that you need to. It's like, imagine you do linear algebra. You try to calculate, calculation based on 2 to the 100 by 2 to the 100. it's going to take you forever, right? Like it's impossible. But this is literally like what a quantum computer should do. And of course, previously we're not even sure that quantum computers can do literally the thing that quantum computer does better than just a classical simulation. So there we can give it to Google, be like, hey, for the first time, your quantum computer is faster than a simulated quantum computer. So that you can argue it's a milestone. But to say that this is like some essential computation, it's kind of silly.
It's not really. It's not a fair competition, right? Like if you're having a competition between classical and quantum computers, you're literally choosing a problem that the quantum computer does just by existing, and a problem for which the classical computer is completely like kneecapped, and making it sound like it's superior, but yeah, it's not a fair competition.
Yeah. Like I'll give it an analogy, right? Like imagine I'm trying to run a simulation of air molecules, like and then I get this box of air molecules in my hands, and I gather data about this box of air molecules, and I claim that it's a air molecule computer. No classical computer can simulate this air of molecule better than my air of molecules. In fact, I have 10 to the 30, 10 to the 26 air molecules. It will take you multiple ages of universe to sample this box of air molecules. You know, then do I claim computer supremacy, like air molecule computer supremacy, my box of air? Maybe I should get a Nobel Prize because of that, right? Like that's the level. I mean, it's a little better than that. I would give it to you, right? It's a little better than that, but like in essence, it feels like that's where we are.
That would be such a good April Fool's Day archive submission. Claim supremacy in the realm of air molecule simulation with my box of air molecules.
Yeah, that would be amazing. So I guess Tim, I'm gonna ask you about your favorite part of the the blog post they made. Is about using computation from parallel universes. Is that actually happening?
Yeah, and when I read the press release, like my jaw just dropped. It's like they say they claim what is it? They prove that there's parallel universes or something insane because their computation is larger than the age of the unit. The computation would take longer than the age of the universe. I mean, I don't know who wrote that. Like, no physicist will think that's a reasonable statement to make.
David Deutsch said that.
Oh, and wait, but they're not quoting him, right? Like,
I think they are. Unfortunately, I think they are quoting.
Oh my gosh, But hey, if that's showcasing universes, parallel universes, how many parallel universes is in my box of air molecules? You know, I think we go straight to time travel right now. Like it's.
Yeah.
I don't even know what to make of that. Yeah.
It's accessing parallel universes to the same extent that every quantum mechanical interaction in every single particle may also be accessing parallel universes if you subscribe to the many worlds interpretation of quantum mechanics. Literally, that's the extent to which that statement is true.
Yeah. I see it more as an interpretational statement, more than like, oh, this is a fact that we're using parallel universes.
Yeah, but that interpretational statement, if you apply that to the quantum computer, you would also have to apply it to the quantum computer that's computing literally the physics in my hand. There's no sense in which Google's quantum computer is accessing parallel universes in a way that's different from like normal physics might or may not be accessing parallel universes.
Yeah.
So
that's totally fair.
Yeah, and I think it's just how silly that statement is. Like, just because a computation will take so long, then they claim, and the fact that they are able to do the computation, then they say that they're accessing parallel universes. Like, every nuclei that's not just hydrogen, like every carbon nuclei, oxygen nuclei in your hands, the mass of that nuclei, if you were to compute it, in a lattice calculation will probably take you forever and forever, basically. So like if you think about that, every atom in your hand is a supercomputer then. Like to calculate the precise property of that, it will probably take you the age of the universe, right? And like in that sense, every atom in my hand is accessing parallel universes. Like it's just
Oh yeah, it might be a good time to plug. Like we had a previous episode entitled "What is the universe computing?" Because there is growing theoretical interest in viewing the universe as a kind of quantum computer, right? That computes like literally. When we use physics to calculate trajectories, you can imagine that there is some meta computer that's actually responsible for realizing this computation, and that's what physics actually is. So yeah, if you to the sense that in the sense that you could literally imagine atoms, like physical atoms, as being a kind of quantum computer, then we are accessing parallel universes all the time. And David Deutsch is a smart guy. Have to believe that he's 100% aware that this was a statement used to generate clicks on Google.
One would hope. So Tim, what you're saying is that like our hands have true quantum supremacy over computers.
yeah, I think so. Every single hand that you have, it's got a bazillion quantum interactions, electrons and atoms and quarks and gluons. It's a quantum supercomputer.
Yeah. So I guess like what I want to ask you both. Now that we've kind of, for lack of better words, dunked on Google's, press release, where does this leave us? I guess, Mikey, I'll point this question to you. Like, where, what do you feel are the next steps?
The next, just really trying to get beyond the current hardware restrictions. Where does this leave us? I guess when I read the article and understood it, I felt like we were, in a road of, 1,000 steps. I feel like we're about half a step further today than we were, 2 months ago. What's next? Honestly, I don't think anyone has a good idea of what to do next. We're literally playing, like you said, we're playing with vacuum tubes right now. And we're demonstrating that we can do like 1+1 with a vacuum tube. It's going to require some giant leaps of ingenuity to move from vacuum tubes to any kind of like usable, reasonable technology that would actually warrant getting excited about in the way that they advertise.
Tim, do you want to take that question as well?
Yeah, I mean, my sentiment is similar. I mean, certainly not an expert. I think academically it's an interesting result, and certainly it's good for driving research funding to academic institutions. But I think certainly people shouldn't focus so much on these big tech companies, Google and probably others. Just say, oh, he is this and that. The real meat that's happening is I think in academic research arena to trying to find new kinds of materials, new kinds of quantum mechanical properties in materials, and how to overcome these complete bottleneck. Still the coherence time is too low. Like, it's not practical. The error rate is still too high, even though it's a factor of 2 reduction per additional qubit. There are still fundamental roadblocks, and so, while it's an interesting milestone, people should not, get ahead of themselves too much and overhype it to the extent that saying that like they're gonna break encryption, like cryptography, like that's just nonsense, right? Like steady research, one step at a time, academically. And people need to set realistic expectation. Like it's still many decades away, quantum computer.
Yeah, no one has a good idea. Like if you ask even like me and Tim are probably more knowledgeable about it than the average person just having a physics background. But if you talk to people working in the field and you ask them what's the next step, I would challenge anyone to give a a satisfying, optimistic kind of answer to that. No one that I've talked to has like a clear picture for what would be the best next step after this.
Yeah, that's fair. Also, Tim, this factor of two reduction is only so far applicable just for the specific hardware that Google's using, which is the superconducting thing. It's unclear with other architectures if the same thing would follow. Is that your understanding as well?
Exactly. Yes.
No, well,
Yeah.
I would say that you could argue that the principle demonstrated on this hardware, like, because they said what they demonstrated was really like an in principle demonstration, and they set up something called the surface code, like a specific algorithm that they're using to achieve this error reduction, and that could be considered platform agnostic. The principle that they've demonstrated, you could imagine doing that, on more sophisticated hardware that works better and getting a better results. But as Tim mentioned, that is the fundamental bottleneck, the hardware restriction.
I see.
And they've done
I
nothing.
see.
They've done nothing to battle that.
Yeah. So we're almost at time. So I wanted to give you guys a chance, in our tradition, to leave the audience any words of wisdom that quantum supremacy has taught you in this quantum computing news.
How much does this make me think that investing in quantum computing startups is a good idea, as opposed to 2 months ago? 0%. 0% more confidence. Yeah, don't throw your money away. Yeah, if it's time, trust me, I think we might be like the first ones to sound the alarm, but this is not it.
Wait, definitely not investing advice one way or another, but yeah, but I don't have high hopes for. I mean, I have high hopes for the long-term future, but for the short-term future, I don't think anything has changed fundamentally before the announcement or after the announcement. And one thing to know is that if you use enough buzzwords, things like parallel universes and quantum physics, hey, people might just throw money at you, and stories of stories of life, I guess.
That is probably the most consequential result of this whole thing, isn't
Probably. Yeah, and then I'll throw in some also concluding thoughts as well from more like cryptography side of things. Is that, like, a lot of people fear that, if we eventually get quantum computers, you'll be able to break RSA, you'll be able to hack in like many different systems. But there are certain classical problems that quantum computers cannot solve efficiently, such as all the NP-complete traveling salesman problem. It means only able to theoretically show results in like solving, say, search, as you're mentioning, Mikey, and also prime factorization, as you were mentioning, Tim, in a more efficient way than classical computers, which is not the span of all possible classical problems. So most likely, if we do develop a large-scale quantum computer, it's probably going to be useful for like, simulating, different physical systems itself, rather than like applicable for like, solving all these like, breaking into, getting secrets and stuff like that. So, and I also, other people who studied this also have similar thoughts as well. So that's it on my side. So, yeah. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you all. Bye-bye.
Bye-bye.